Hi, I'm going to talk about question number 8, which is part of ionization practice set number 2. And this is the one where a dog ingests strychnine, which is a weak base with a pK of 9.4. And we're interested in knowing between two compartments, the duodenal lumen with a pH of 6.4 and the plasma with a pH of 7.4, where's this drug going to move? And effectively what we're saying in the terminology of the question says, what percent of the ingested dose of strychnine would you expect to be absorbed from the duodenum? We know that absorption means going from the site of administration, in this case it was ingested and it made it down to the duodenum, into systemic circulation, the plasma. So it's really just a word problem way of saying how much drug will be in the plasma at equilibrium. Now, part of what makes this question tricky is we know that a weak base is going to have a predominance of ionized particles over non-ionized particles in a relatively acidic environment. And when we look at these two compartments, both of them are acidic relative to this drug's pKa. So both of them have a lower pH than the pKa of our drug or toxin. So that's what makes these numbers look a little different than what we're used to seeing, but the math is the same and the way we look at it is the same. So if we take our duodenal lumen with a pH of 6.4, and then we have plasma with a pH of 7.4. On this side, if we do our 10 to pK 9.4 minus pH 6.4, this is a weak base, so drop that base, I over N, or bin, B-I-N, I over N. We are going to have 9.4 minus 6.4, so 10 to the 3 equals I over N, so 1,000 over 1 equals I over N. All right, and does that make sense? This is a pH of 6.4. It is relatively acidic compared to the pK of 9.4, so the ionized form should predominate. I should be the bigger number. 1,000 over 1, yes, ionized, I is the bigger number, so it all makes sense. On the plasma side, likewise, we've got our pK of 9.4 minus 7.4 equals I over N. So in this case, 10 to the 2 equals I over N. So 100 over 1 equals I over N. Same idea. The pH here is still lower, more acidic than the pKa of the drug, but not as much. So the I predominates, but not by as great a degree. So once we have figured out the N to I ratio in each of our two compartments, now we want to compare the two. So our next step is always going to be setting the N's to equilibrium, which means setting N equal to 1 and figuring out what is the ratio of I when N is 1. Well, in this case, our N's are already 1 in both of these, so we don't have to make any change. We just have to keep our N's and our I's straight. So for every 1 N on the duodenal side, there's 1,000 I's. And then for every 1 N on the plasma side, there's 100 in the ionized state. All right, so once we have gotten our equilibrium set, now next step is basically we've just described that if we took a snapshot and stopped time at equilibrium, for every 1 part that's non-ionized on the duodenal side, there would be 1,000 parts ionized on the duodenal side. There'd be 1 part ionized on the non-ionized on the plasma side. There'd be 100 parts ionized on the plasma side. And so by doing that, we now can look at total proportions on either side of this membrane. So take these away, clean it up a little bit. So on this side, we have 1,001 total particles. On this side, we have 101. So the total parts that we're dealing with is 1,102. And at this point again, once we get to our equilibrium distribution, now all we really care about is how much total drug is on the duodenal side of this membrane, how much total drug is on the plasma side. We have 1,001 particles on the duodenal side out of a total of 1,002. And on the plasma side, we have 101 out of a total of, 1,102, not 1,002. And so if we want to figure out proportion, we just divide those, and what we've got here is about 90% on the duodenal side and about 10% on the plasma side. Now, this is maybe counter what you are expecting, so we kind of, whenever we're looking at plasma, duodenum and plasma, we're kind of expecting, oh, this is probably going to move in the plasma. And in this case, what we have is the opposite. If these reach equilibrium, the majority is still sitting in the duodenal lumen, meaning only about 10% of the amount he ingested got absorbed into systemic circulation. So the question was, how much will be found in the plasma at equilibrium? So the answer to that question is 10% will be found in the plasma. Now, think about what that means. This means if the dog ate, a certain amount, if we say he, 100 milligrams of toxin made it into the duodenum, then that means 10 milligrams of that made it into the plasma, if 10% of the drug made it into the plasma. So it's a small amount, but when we're talking about a very potent toxin, that might be enough to actually be toxic. We don't know. So in this case, this is obviously a simplified version of what's going on, but it illustrates how the math will still give you the same answers. Now, if we want to look at question number 9, it's basically the same scenario, only in this case, the dog received, I'm actually just going to leave this here on the bottom. Now, in this case, the dog has received an alkalizing agent that changes the duodenal pH. So the plasma pH, that's going to stay the same. Now our duodenal pH has increased to 8.4. So it's no longer 6.4, it's now 8.4. Now notice how much closer that is to the pKa. If this duodenal pH was 9.4, then we know it would be 50% ionized, 50% not. This is still slightly more acidic than the pKa of the drug, so we know that the ionized will still predominate. But now if we do our 10 to the 9.4 minus 8.4 equals I over n, we're going to have 10 to the 1 equals I over n, 10 over 1 equals I over n. So now we're just dealing with a different proportion of the I to n. And on this side of the equation, we still have, the pH didn't change in the plasma, so we still have 100 to 1 equals I over n. So again, we would want to set our n's to equilibrium, n's both equal to 1. And again, in this case, n's are already 1, so the n to I ratio here, for every 1 n, there'll be 10 i's. And on the plasma side, for every 1 n, there'll be 100 i's. So by shifting that duodenal pH, you can see how, even though we're still working in relatively acidic environments, it's shifted just how many of those non-ionized particles are around to move. And once we have this equilibrium set up, now we can say there's 11 particles on this side for every 101 particles on that side. So we're dealing with 112 total parts, total ways it can be. And proportionally, 11 over 112 equals, it's going to be somewhere around 10%. And 101 over 112 is going to be somewhere around 90%. So now the question again was how much has been absorbed into plasma. So we're looking at how much is over here. Now the answer is 90%. So by increasing the duodenal pH, bringing it closer, more alkaline for this weak base by using an antacid drug, we have actually now increased the proportion of this toxin that gets absorbed. So again, if this patient had eaten 100 milligrams, 100 milligrams got down into the duodenum, then 90 milligrams of that will have made it into the plasma, and only 10 will be left sitting in the duodenum. Now you'll notice when I do these, I tend to calculate each of the two compartments, and they should always add up to 100. So 10 plus 90, 90 plus 10, you should always have 100. And then the question is always going to be where's more, how much drug is in place A or place B? So you just then need to interpret what the question's asking. If we're talking about absorption, we're saying move from the site of administration to the plasma, or as it states right in the question, how much is in the plasma at equilibrium. But you can also see for strychnine, which is a toxin that is a weak base, if you gave an antacid, that actually would enhance abdominal absorption. So this is one of the few toxins where we try to avoid giving antacid therapy if there's still material in the GI lumen because it may enhance absorption. And if you want to go one step further, think about what would happen if you alkalinize or acidify the urine pH. So in this case, if you alkalinize the urine pH, it's also going to enhance absorption, but that's reabsorption back into the bloodstream, which will keep the toxin around longer. So we want to acidify the stomach to prevent absorption, or at least just let it be acidic, and we'd prefer to acidify the urine to enhance excretion. So if you have questions about this, let me know, but this one is, I would say, more in depth than the type of thing I would ask on your quiz. So good luck, everyone. Bye-bye.